All right, left and right Cosets. So if we've got our subgroup H from original group G, and we've got some element in G. So we've got subgroup H, some operation star of G, and some X element of G, then we can define different sets of elements by using our operation with X and the elements of H. So the left Coset is when I combine X on the left. So XH is a shortcut notation for X star H. So notice not multiplication, X star H for H element of H and X element of G. These are the left Cosets. Because I've got all of my values of G, all of my elements of G, and some of the values of H, some of the values of G from H, by defining all of the left Cosets, eventually I'll define all of the values in my original set G. We're going to look at that some more down here. Right Cosets, just doing the operation in the opposite way. So H star, sorry, this should have been a lowercase h. So H star X, again, H is an element of the subgroup H, X is an element of the original group G, and this is the right Coset. So this makes more sense when we look at an example. So let's look at the example. And through this example, I'm going to explain how we can use Cayley tables to determine our Cosets. It's probably the easiest way. So we've got a subgroup 3z. So these are our multiples of 3 within integers over addition. The original group was all of the integers and addition. So if I think about a Cayley table, let's think about our left Cosets first. So our left Cosets, we're looking at x3z. All right, so what this really means is x plus 3z for every element of z plus every element of the multiples of 3. All right. So if I think about making a Cayley table for this, we've got addition. And if we're looking at our operations here, our values of x are going to go on our left-hand side. So obviously this is a whole group of integers. I'm not going to list them all. I'll just start with 0, 1, 2, etc. So I could keep going. Across the top, I've got the right value in my operation. So my multiples of 3. So negative 3, 0, 3, 6, for example. Obviously, these could keep going. All right, so let's fill in some values. We've got addition, so here's our identity. Our identity. All right, so this is going to be negative 2, 4, 7, negative 1, 5, 8. Notice I'm going to end up covering all of my integers, which should happen. I should cover all of my values of z. So our Cosets, we've got 3 unique Cosets because at this next point, if I continued going on, so if we went down here to 3, then our next value is going to be 0, 3, 6, 9. So notice we've started repeating. So these are going to be identical because we keep going on, right? This is not a fixed table. We've got infinite groups. So we've got 3 left Cosets. So our set of all elements, we've got 0 plus 3z. So that's going to end up giving us negative 6, negative 3, 0, 3, 6, so on and so forth. So these are all of our multiples of 3. Then we've got 1 plus 3, 3z. So we're going to have all of those shifted by 1. And then we've got 2 plus 3z. Oops. So we could also say these are our 3 partitions of our original set of integers. All right, so these are our left cosets. Well, addition is commutative. So our right cosets are going to be 3zx. Of course, that's going to be the same as 3z plus x. Those are going to be the same. So the right cosets and of course, again, that's because addition is commutative. In our next example, we're going to look at a case where the operation is not commutative and look at the different left and right cosets.